issues did you have? Maybe you don't have any, which is fine. Was there anything that we need to look at from the homework with the ratio test? You do it a few times, it's pretty straightforward, isn't it? Wow, no complaints? We could just roll right into the quiz? Wow, this might be short. Yeah, because we need to finish early so that some people are trying to get their room assignments for next year, apparently. But anyway, yeah, let's do this. That way, the quicker we go, the quicker the better. So here, I'll put it up on the screen, but I'll give you one copy in just a sec. So yeah, you can't see it anyway. It's just for Ben. I'm going to go to the back because I always say that I'm going to, and I always forget. There you are. See, I do care. There's some. Here's 3, I think. There may be 4. It doesn't matter. Here, we'll give one to. Here, there's a few. There's 2. I know that we want one more though. So here's one more. There's 2 there. Make sure you share. There's 1, and here's 4. Uh-oh. 1, 2, 3. There's got to be extras somewhere. You've got an extra. Good. Is there one more extra? Good. Oh, I'm so happy. I was worried that I didn't have enough. There's one for you, and you need one over here. Well done. Okay. Hey, before you hand this in, I see people are already ready. Make sure that when you're doing these, that you make it super obvious. You can do like a, I don't know, like a big D or diverge. If you've already boxed it, just make sure it's really obvious. It'll make it easier for me. C, diverge, converge. Pick the one that is appropriate. Anyway, yeah, just put a box around whatever your answer is. I mean, I'll be looking at the whole thing, but just make it easy for me. And I think I've returned all the exams except for the absent person. Is there anyone that I didn't give an exam to who deserves an exam? All right. So be sure. Got a few people from my other class too. I should actually do this. All right, well, I've got mine all written up. If you're done, feel free to turn it over, pass it over. If you're still working, it's okay. But hopefully you're wrapping things up. Beautiful, nice. Oops, you're still thinking. You're doing it. Good job. Good job. Still thinking. You're done. Nice work. Excellent. Thank you. Look at this nice little stack here. Just thinking, that's fine. It's good. Meditating. Very nice. I like the way you did that. Very good. You're still meditating on that one? Okay.
When's the alt meeting? I remember you saying you had to have to add this just in case. I know it's gonna be the same answer either way.
Well, then you're fine.
Okay.
In this case. Yeah, we'll talk about it. I'll keep my, yeah, I'll let you know. All right, hopefully you're wrapping things up. Finishing up that last one, doing the canceling. Looking good. Nice. Looking good. All right, good job. Very nice. All right, try to get something down for that last one. So I'll come get what you have here in just about 1 minute. If you haven't finished, wrap it up. Just meditating, I see. You could always box your answer, or you could leave it like that and make me suffer. That's fine. Excellent. Yeah. Doing it. You're doing it. Nice. Well, Fred, what do you think? Just, yeah, put that last word there. That's good. Okay, you got something? Very nice. Good job. Good job. All right. Very nice. It's not fully done. You have a limit, and you have a word. Yeah. Right. Good job. What do we got here? No. You got one over there. Just trying to gather up the final things. I think there's one over here. Is that for me? All right. You're. Oh, I see, and I didn't see it. Very nice. Very nice. Good job. Good work. Well done. All right. I think I've got. Oh, Simon, thank you. Any others? Oh, Daniel, holding out on me. Did you change anything in the time that you meditated? No, you just looked at it. That's fine. Okay, I've got them all now. I got them all? Okay, good. Let me staple these together, and I'll show you mine. Here, I'll just unfreeze. Look at my first one. So the first one, just to remind you, the ratio test, we're making a ratio, and you'll notice that I left off the -1 because you're doing the absolute value, so the -1 is going to go away anyway. If you left the -1 there, that's fine, but in this case, it just goes away because of the absolute value. We'll talk about that -1 though, because I was kind of hoping one of these would be conditionally convergent, but that wasn't the case. I just typed these up this morning, and I made a slight error, which is fine. But anyway, getting back to this, so this one is absolutely convergent because when I do that limit, if I've done all my canceling correctly, which I think I did, let's see, we get n plus 3 times 2 to the n over n cubed times 2 to the n plus 1. So the 2's cancel, all but one of them. And then do the limit of that fraction. This would be n cubed plus 3n squared plus 3n plus 1. Anyway, that's going to be 1 over 2. So that's less than 1. That's the comparison you're doing. So that one absolutely converges. So whenever the whenever this test comes out as being less than 1, you're absolutely converging. This one, we did something similar. Factorial, I know, is really annoying, but I didn't show my work. Maybe I should. Here, I'll show my work. Just a sec. So just so that you can see what happened. So it's -3 to the n plus 1. And you could just drop the negative because we're doing the absolute value. So this will be the limit as n approaches infinity. This will have an n factorial there. This is n plus 1 factorial times 3 to the n. So anyway, from here to here, all I did was I just flipped this one and multiplied. And I got rid of the negatives because -3 to the n is the same as 3 to the n if you're doing the absolute value. Anyway, now you can see that a bunch of the 3's are going to cancel, so that's easy enough. Cancel all but one of those 3's. And then in terms of the factorials, n plus 1 factorial is n plus 1 times n factorial. So that cancels with this, and you're left with just 3 over n plus 1. So this will be the 3 over n plus 1, or negative, doesn't matter because I'm doing an absolute value. And anyway, the limit as n approaches infinity is going to be 0. So this one converges, converges absolutely. If you just wrote converge, that's fine too, because it does converge. So this one converges absolutely as well. So both of these are absolutely convergent. Someone asked me, well, what's up with the -1? Okay, so here's the deal. I didn't create a good one. Let me see if I can make one here really quick. What if we do this? How about -1 to the n over n? I don't know. This isn't, I mean, this is kind of boring, but yeah, here's the difference is that if this was the problem, then this thing, when I did my limit of 1 over n plus 1, 1 over n, I would get 1, which means I don't know. So I don't know if this converges or not. I have to go back and actually examine it more closely. So this one actually, this converges because it's an alternating series. So this converges, but if you get rid of the -1, if you just make this 1 over n, then it diverges. So that's why that's called conditionally convergent. So absolutely convergent is all of this stuff over here. Yeah, I meant to have one that was like that, but I didn't. So anyway, if you converge. If you have converge for both of them, you're good. If you have diverge for one of them, I'll look at it and see if I can figure out why you thought it was divergent. It could have been algebra. I mean, if you do your algebra wrong, there it is. Okay, so today what we're going to do is we're going to examine another test. It's going to be a quickie called the root test. Let me just explain sort of the basis or why one way to think of this. You remember last time I mentioned that one way to think of the ratio test is that you're checking to see if you are close enough to a geometric series to say that you converge. So let's take a look at this geometric series. And let me point out that there's a couple of different ways to figure out the value of r. So one way, this r, this ratio, common ratio, in a geometric series, one way is to take a sub n plus 1 and divide it by a sub n. In this case, we could just pick two successive terms, 1/16 and 1/8, for example. 1/16 divided by 1/8, if you do the math, is, whoops, not 1/8, sorry, is 1/2. So the common ratio here is 1/2. And that's kind of like the basis for the ratio test, is that you're saying, is this sequence close enough to a geometric sequence to say that the series converges? Now, another way of looking at this is that series is this, 1/2 to the nth power. I mean, that's what the terms are, right? This is 1/2 to the 0 power, 1/2 to the first, 1/2 to the second, 1/2 to the third, and so on. And so another way of looking at this is that the ratio is the nth root of a sub n. So if you take the nth root of the nth term, you get the common ratio. So let's take a look at this term here. That is the fourth term if you start counting at 0. 0, 1, 2, 3, 4. Do the fourth, let's see, the r is the fourth root of 1/16, which if you do it on your calculator or if you can do it in your head, which you should be able to, the fourth root of 16 is 2 because 2 to the fourth is 16. So there's another way of arriving at the common ratio. So that's basically it, and that's the root test. The root test is this. Oh, let me write it out, and I'll go back to the PowerPoint so you can see it formally written, but that's pretty much it, is that tonight you're going to be doing this. The limit as n approaches infinity of the nth root of a sub n. And if that is less than 1, so if that's less than 1, then you converge. If it is greater than 1, you diverge. And if it's equal to 1, you don't know. So that's it. So let's, I'll go back to PowerPoint though, so you can actually see it written, but that's pretty much it. Let me go back here. Yeah, there it is. There's the root test. So this is what you'll see in your book if you find the correct page in your book. It looks a little bit more complicated, but let me point out the important stuff is that you're doing this limit. So let me get the important stuff here is, whoops, where is this? There we go. Okay, so here's what you're going to do. If you want to write something down, write this down. So if the limit of the nth root of the nth term is 1 or less than 1, then you converge. If you can remember that, I think the rest of it is easy because the rest of this is just like the opposite. If it's greater than 1, you diverge, and if it's equal to 1, you don't know. So I mean, honestly, what I just highlighted, that's all I would ever memorize. I mean, why? I'm not a biologist. I'm not going to memorize a bunch of stuff. So just try to remember the most important stuff, and then you can figure out the rest. So if you remember this stuff, hopefully you can figure out that, oh, if it's the opposite, you're diverging. And then, of course, you have the edge case, which is the inconclusive one. So I'll give you a minute. You can look at that, and then we'll take a look at an example. Yes, sir. Well, then you have to examine, like, do other stuff. So that's the problem is the flow chart that we have, which I need to go back to. But if we put at the bottom, which we could, the ratio test and the root test, if those are inconclusive, essentially what I do is I go back to the top. And I ask myself, maybe I missed something in terms of the comparison tests or in terms of something else. So yeah, so if you can't, if it's inconclusive, I basically restart. And yeah, because this is we're at the bottom of the tests here. We're all done. This is the last one. So on Friday, we get to do power series, power series. So it's exciting. But yeah, by the way, power series is the reason why we do this stuff is we need to have some way of determining when a power series converges. You'll see what I mean on Friday. So we're finally getting X. X is coming back. I'm very excited. But anyway, let's see what we can do here. So let's take a look at this example. This is the sort of series that really lends itself well to the root test. You'll notice what's special about this is that you have an exponent, an nth exponent. Anytime you have something raised to the n power, you should think, wait a minute, I would probably do better if I did a root test than if I did a ratio test. So imagine doing a ratio test with this. It would be a big pain. Yeah, it's just going to be ugly. So doing a ratio test with this would be ugly, but a root test is not bad at all. So let's do the root test. Whoops. Let me get a pen that looks good. How about this? So we're going to do the limit as n approaches infinity of the nth root of that. So that's what you're going to be writing down. Basically, you're going to do the nth root of the term. So you don't have to deal with the n plus first term. However, I mean, certain things are going to be easier using the ratio test, certain things for the root test, but we'll do our best to sort that out. But anyway, getting back to this, let's go ahead and do this. So this is going to be, oh, sorry, I got to put the absolute value symbol in there. So if you didn't do it, like I just didn't, add that absolute value symbol. It's not an issue here, but the problem is that you cannot do a root of a negative number. You can't do an even root. So like a square root of a negative number is going to be imaginary. Yeah, you don't want to deal with that. At least not in calculus. We're dealing with real numbers here, all right? You can take another course to do your imaginary business. Okay, so this is going to be this. So since there's nothing negative in there, I can just drop that, the absolute values, and then the root, here's the key here, is that if you have an nth root of, let's just call this q to the n, you get just q. As long as q is non-negative, so that's the key. I cannot have a negative number here. Now you might be worried, like I know that you're probably thinking, wait a minute, I thought that when we did the square root of x squared, we got plus or minus x. No, that's not what happened. What happened is that the square root of x squared is the absolute value of x, because x could be a negative number. And so that's the deal there with something like this, is that if you have a negative number down here and you do this square root. So, but we're saying that this will never be negative, so you don't have to worry about that thing happening. So here we go. So let's stick with this here. So in other words, I'm just going to focus on the stuff in the parentheses there. So this will be 2n plus 3 over 3n plus 2. And now you can do this. Let me just find a volunteer here. Here we go. So Ethan knows. Ethan, do you know the limit of this thing? Limit is n approaches infinity. It's a polynomial over a polynomial. You take the... Very good. Yeah, it's 2/3. Very nice. Yeah, so yeah, I know I'm hitting him up early. He's still waking up. So you'll be better later on today. Very good, though. You got it. You got it in the end. That's what's important. 2/3. I knew you could do it. Yeah, this is just polynomial over polynomial. You have the same degree, and so you take the leading coefficients. Well done. 2/3. Now, this is the root test says it's the same as the ratio test. As long as this limit is less than 1, then you absolutely converge. So absolute converge, absolutely whatever, converge. Yay, absolutely converge. So let's try another one of these. There we go. Two more to do. Good. So I'll let you do these. Wait, what are these? Determine the series is absolutely or conditionally convergent. Yeah. Yeah, try both of those and see where we go. Look at that, they're giant sized. Sorry, I'll get it back up there in just a sec. Just making room. Okay, we'll do this one first and we'll do the other one. So sorry if you're excited about the second one more than the first one, but here we are. All right, so Hunter, tell me what to write here. I've got the limit is n approaches infinity. What do I put over here?
The nth root of e to the negative n
In factorial, very good. And I'm just going to put this, even though I know it's all positive, but just for completeness, I'm going to throw the absolute value symbols in there to make sure. Let's go ahead and simplify this a little bit. This is going to be the limit as n approaches infinity of the nth root. So just to make things easier on us, of n factorial over e to the n. So at this point, I don't know if you're in the same boat as I am as you're looking at this, but at this point, I don't want to go any further with this because I can certainly do the nth root of e to the n, but it's that n factorial that's causing me a little bit of grief. How do I do the nth root of n factorial? I'm having a problem. So at this point with this one, what I would do is I would say, you know, I don't want to do an nth root. I'm going to do a different test. So this is what I mean by, you know, what do we do if these are inconclusive? Is the same thing I'm about to do now is I'm going to go find another way. So if you get stuck like this, I'm stuck. I'm not saying that this is impossible to deal with. I'm just saying that I don't want to deal with it. So I'm pretty sure that I could deal with it. It's just not fun. So I'm going to do it another way. So let's do the second one, and then we'll come back and I'll explain what I'm going to do when I get stuck. So don't worry, we're coming back to this. I'm not going to leave it here. We're not going to leave you hanging. Some of you know, I think some of you know what we're about to do with this one, but we'll come back to it. Let's do this one. So if you haven't done it already, I know I changed the screen for a bit there. So take a minute and crank this one out. All right, let's see where we are. Who's my volunteer? We got it here, Christopher. What do you have here for your limit? What limit are you going to put down? All right, so -1 to the n over natural log of n to the nth power. Now this one I'm more optimistic about. I don't know about you, but when I see this, I know there's a lot of n's there, but that one looks to me like something I can deal with. And in fact, I'm going to deal with it because you can do the nth root of an nth power. In fact, let's go ahead and do that. So this is going to be the limit as n approaches infinity of the nth root. First of all, the absolute value means that that numerator is just 1, right? Because if this was -1 up here, like an odd power, you'd have -1, but you're going to do the absolute value, which gives you +1. If this was +1, then of course it's just +1. On the bottom, I have the natural log of n to the nth power. So now we're going to just drop, well, here, I better write it out. I think you probably know what it's, but I'll write it. Okay, now I can drop everything. Limit as n approaches infinity of 1 over the natural log of n. Wait, where's my original sum? Oh, that original sum diverges. There, now it converges. Sorry. Well, I'll show you what I did. I don't know if you saw. I fixed something that was a problem. Okay, so let's get our volunteers for this. So we have Ryan. Ryan, what do you think of this? Does this converge or what is the limit? Yeah, that limit is 0. 0 is less than 1, right? 0 is less than 1, which means the conclusion is that this thing absolutely converges. So very nice. So yeah, the thing I changed back here is I realized that if n began at 1, notice what that is. You get natural log of 1 is 0, so you'd have 0 in the denominator right off the bat, which is a no-no. So yeah, I changed this to 2. Then you're okay. But yeah, this particular test is checking for what is happening, like that direction, sorry, way out at infinity. It's not checking the beginning. So if you begin badly, then you're stuck, I guess. But it's more concerned if we add together a whole bunch of terms, what's going to happen? Is this going to converge or diverge? Let's see. So there it is. That's good. Oh yeah, I said I was going to go back. So what do? We're stuck. We're stuck. Well, we're not really stuck, are we? Does anyone have any suggestions about how to deal with this? Yeah, what do you want to do, Hayden? Yeah, ratio test. So I mean, I think all the homework problems for Friday are root test problems. But if something is better with the ratio test, it doesn't mean that you can't use a ratio test. Let's go ahead and use the ratio test with this one. So let's go. This is going to look like this. So e to the negative n plus 1 factorial. Oh yeah. No, you do you. No, yeah, fractions. I agree. You write it as a fraction, the e to the negative n, put it on the bottom. That's fine. But yeah, I just wanted to write it. So you do whatever it takes. Little practice with this. So if you didn't get it right on the quiz, here's another one you can do. Practice. See if you can get it right here. All right, I'm going to go finish this up. Well, get most of it done. I'll have someone help me at the end. I'll explain what I'm doing in just a sec. Okay, so what did I just do? First of all, these negatives. So this is what Hayden was complaining about, these negative exponents. So if you wrote it in fraction form, that is to say, this is n factorial over e to the n, then this would look a little bit better, but I've fixed it over here. It's fine. The negative exponent just means it's in the wrong place. It belongs up here. This one belongs down here. So that's what I did. Then I also took n plus 1 factorial, and I rewrote it as n plus 1 times n factorial. You might remember that whenever you have n plus 1, well, factorials generally are going to lend themselves well to the ratio test. So now that I've got that, let me cancel what I can. So this will equal the limit as n approaches infinity of, let's see, this stuff cancels with that. This cancels with this. This is n plus 1 over e. There we go. That looks good. Ah, yes, I see. So let's find someone to do this limit for me. Karen, do you know the limit of n plus 1 over e as n goes to infinity? It is infinity. Very good. So this one diverges. I guess I could write that like that, but that is definitely greater than 1. And so this thing diverges. By the way, I guess I should be careful about this. Let's just back up for just a sec. If this thing were an alternating series, if you get if this thing diverges when you put the absolute value symbol on, you should go back and ask yourself, if this were here, let me just show you what I mean. Let's say that this was negative e, there, negative e to the negative n. Now I've got an alternating series, and so I would have to check, does this converge as an alternating series? So you would have to do the alternating series test. So here's what that would look like. Just a minute. I'm going to make Hayden happy. Write it as a fraction. So anyway, so does this converge? So you remember the alternating series test. So let's actually do that. So this thing diverges, at least when you put the absolute value symbol on. But if you diverge, if you have an alternating series, you still have to go back and ask yourself, well, what if we leave that negative 1 there? Let's do the alternating series test. Use this. B sub n is n factorial over e to the n. So this thing is greater than 0. Does this decrease? And then what is the limit? Well, let's just do the limit, and then we'll worry about decreasing. So what's the limit as n approaches infinity of this? So find a volunteer here. Caleb knows. Caleb, what do you think? Is this thing gonna, what's the limit of this? Do you have any guesses? Let me rewrite this for you a little bit. Might help you. So this is the limit as n approaches infinity of n over e times n minus 1 over e times n minus 2 over e, because there's the same number of things here. It's n times n minus 1 and so on, all the way down to 1. And this, there's a bunch of e's. So when you look at that, what's your instincts as to what the limit of this is going to be? Yeah, infinity, because of like this first term in particular. As n gets bigger, n is going to just dwarf e. And so, yeah, that's going to be infinite. So, yeah, that diverges. That goes to infinity. And so you don't even have to worry about decreasing. It's not decreasing. It's actually increasing. But so this thing, this one, if this were the series that we were looking at, this not only diverges, absolutely, it diverges. Yeah, it totally diverges. There's no conditional, nothing. All right, so let's see. What can we do next? Is we can do this. Let's introduce one little thing. Where is it? Where's my series? Let's see, which one do we want to do this with? None of these are good. Let's, yes? Yes, tell. Which one is this? This one? Oh, wait. Yes. Ooh. Could this work? Just a minute. Like that? Okay. What is the nth root of n factorial? See, that's where I'm stuck. Okay, so I suppose, could I argue that I would know that this diverges some way? See, this is where I'm stuck, is how do I know that that is I mean, that's true, but to prove that, that's where I'm stuck. So I'm not sure how I'm going to say, like, maybe it seems obvious to you, but why is it? Why is this infinity is the question. Can you argue from a mathematical, can you say, well, clearly, because what is the nth root of n factorial? You're taking like 10 here. Let's take a look at this. 10 factorial, and you do the 10th root of that. What is that? It's not something that I can. Oh, what is it? Oh, well, does that matter though? I mean, because then we have to worry about the 100th root. Yeah, you're right though. Is it bigger than 2.71828? You're right. But yeah, so I don't know what that is. So I guess that's where I'm stuck. I said, like, when we got to that stuck part, I said, probably we could come up with a way to deal with this, to argue that this is going to converge or diverge. It's just that it's hard. And it's a lot easier to use the ratio test. So don't feel like you have to use a particular test. If you get stuck or if you get to a point, so I'm pretty sure that we could find an argument to say that, yes, that this is going to be bigger than 2.71828. Yeah, but it's just, in fact, I'm curious, what is the 10th root of 10 factorial? Let me just do this really quick. I don't know 10 factorial offhand. Give me a sec. Prob for... Okay, so the 10th root of 10 factorial is 4.52, but that still doesn't really prove it to me because I don't know what's going to happen in the long run. This limit is saying what's going to happen when you get bigger and bigger. So there's probably an argument that this does keep increasing, and it is infinite. But yeah, I guess here's what I'm saying is that if you get to a point where you're like, I'm not sure where to go with this, there's no shame in picking a different method. So even if you could come up with an argument that works. All right, Thomas. Raise what all? Well, I'm doing this limit right here. Right. So here, let me see. Limit as n approaches infinity of, oh, wait, give me a sec. Yeah, okay. Yeah, all right, well, let's do it. No, this is fine. So yeah, I think this is the way I might do this, is do that. So move, I think this is equivalent to what you're saying. Yeah, so move the limit inside the radical and then say, okay, what is the limit of this thing? The limit of that thing is going to be bigger than 1 because n is bigger than e in general. So you have the limit as n approaches infinity. Let's put that there, of n over e times n minus 1 over e. So as long as times 2 over e times 1 over e. So the only time that this fraction is smaller than 1 is 2 and 1 over e. So all of these are much bigger than 1, right? Like if you have n equals 10 or 15, 15 over e is much bigger than 1. And so there's, yeah, likely some, okay, let's finish it up, I guess. So as long as, oops, I just turned off my screen. Okay, so as long, I know, I just want to make sure that it is correct mathematically. So I'm not waving my hand. So you can, since we're doing it, we're doing it. Okay, so as long as, let's see, as long as n is greater than 2, n over e is greater than 1. Okay, so now we just have to figure out how many terms do I need to multiply to get a number bigger than 1, because I have this 2 over e and 1 over e. So let's see, 2 over e times 1 over e times 3 over e is bigger than 1, 4 over e is bigger than 1, and 5 over e, is that total going to be bigger than 1? Once I plug in these, I guess I need enough terms or enough factors to neutralize these two, because those are less than 1. And I think I probably have enough here. So, well, let's just go one more. So 6 over, here. No, we'll do this. I know this is overkill. Just a minute, I'll explain myself. Because we're doing a limit. Where is my limit? We're doing a limit as n approaches infinity. So give me a sec. This is the sort of thing mathematicians worry about that you guys don't care about as much. Okay, so first off, E is 2.718281828, and so E is less than 3, which means this is bigger than 2. Bigger than 2. So when you multiply those together, you get a number bigger than 1. Wait, is that right? Yeah. Because 2 over E is bigger than 1/2. So those two cancel each other out, so to speak. And then this is going to be bigger than 3. Bigger than 3. And so when I multiply this one times that one, because this is bigger than 1/3, so something bigger than 1/3 times something bigger than 3 is going to be bigger than 1 as well. So once I get beyond 9 over E, you're right. The final, it's going to be bigger than 1. So if that makes you happy there, that was the stuff I was trying to avoid when I said I was stuck. So is that I knew that there was probably a way that we could figure it out that was reasonable, and hopefully you understand what we did here. But now, so as long as, so when, here's what we've concluded, when n is bigger than 9, it turns out that n factorial over e to the n will be bigger than 1. That's what I've just proved. And so then, therefore, the limit as n approaches infinity of the nth root of this is bigger than 1 as well. Because clearly you're dealing with numbers that are bigger than 1 and you're doing the nth root of those numbers. It's infinite, but it's bigger than 1. So we diverge. Okay, let's see. Do I have any energy to do more? It's 10 o'clock already. Oh, get it on there. Get it on there. You doing it? Did you get it? You're doing it. Good. Good. Yeah, I think we need to stop because I want to know. So if you want to find out if they got Maplewood 302 like they're looking for, we can, otherwise, we're just going to stop. Oh, my battery's running low anyway, it says. I'm not properly plugged in. So let me stop the recording.